Okay, so in this final video lecture for this semester, I'm going to try and do a summary of the entire course in around an hour. So I'm going to go rather briefly through these topics, obviously. I will emphasize more the ones that we studied at the beginning of the course, the ones that might be more rusty, and I'll be briefer towards the end, towards the more recent topics. So there are two main blocks to this course. There's the block where we learned about various integration techniques, and then we seem to make a somewhat discontinuous jump into discussing sequences, series, Taylor series, and then these topics all connected together again. So we start with integration. So we learned a whole bunch of integration methods. And the first one was integration by parts. So if we take a product of two functions and we differentiate it, we have this. So then we can put one of these on the other side. So we have u prime v is equal to and then we take the antiderivative of both sides and we end up with the integration by parts formula. Okay, which is a very easy formula to use and to get right if you just take it from the product rule. And the point of this is that there's often some product of functions we're trying to integrate where if instead of dealing with u prime v, we deal with u v prime, then we're in better shape. So you have to, well, hopefully you have learned this ability to look at something and go, okay, I don't want to deal with this guy. I want to deal instead with u v prime. So a classic easy example would be this, right? So if we let v be, let's change colors. If we let v be this guy and u prime be this guy, if we go to v prime, it's easier, we just get 1. And if we go from u prime to u, it's no worse because we just get minus cosine, right? So the option of considering this guy as opposed to this guy is definitely better. And this thing is already just given to us. So you have to have learned this ability. This is one of the basic methods for integration, and that's this entire section. So there's a lot of things we can integrate just by using this particular method. The next method, or the next thing we learned was trig integrals. So trig integrals. So this is when we had some kind of thing like this. Cosine of m to the x, sine of n to the x, dx. And we want to integrate it. So we have a couple of things. We have this thing. We have this identity, sine squared x plus cosine squared x is equal to 1. And we know, of course, what happens when we differentiate sine. We just get cosine. When we differentiate cosine, we get minus sine, right? So what we want to do is to use u sub and turn all of this stuff into either a whole bunch of cosines and a single sine, right? And if we can do that, then we're just going to let u be cosine, and when we're going to use this identity right here. So if, for example, n is odd, so it's 2k plus 1, then we can rewrite this thing as cosine to the m of x, sine to the 2k of x, sine of x, dx, right? And then we have this identity over here, so we have the sine squared of x equals 1 minus cosine squared of x. And we can plug it into this thing because this is sine of 2kx, so it's sine squared to the power k. So then this whole guy here is going to be cosine m of x and just 1 minus x, everything to the power k. And then we just have a sine of x dx, right? And then the natural thing is to let u be cosine of x, because du by dx is minus sine of x, and therefore du, or minus du, is equal to sine of x dx, which is this structure right here. So then we can replace this with minus du, and all of these guys just get turned into u, so we just end up with a polynomial of u, which we can integrate. And that is the strategy for dealing with the analogous case when we have n is odd, right? Sorry, when we just did when n is odd. When m is odd, we'll do exactly the same thing. We'll pull off one cosine, and then we'll turn the rest of the cosines into sine, and then the same kind of thing, right? The only thing that is a bit harder is when both of these guys are even powers, and then we have to use identities. So we have identities for cosine squared and sine squared, and we just have to use them repeatedly. So cosine squared of x, for example, you know it's this, right? And this thing you can integrate. So you'll either have something which has got an odd power either here, or you have even powers, and then you can just use this kind of stuff. This isn't particularly difficult. It's not, what I want to say is the way to do this is not to try and memorize these various rules. You just have the same strategy all the time. You're just going to use u sub, and then these identities. We also have an analogous thing when we have tan and sec, and then the identity is that sec squared of x equals 1 plus tan of x, and when we differentiate tan, we get sec squared, and then when we differentiate sec, we get sec tan. And then using exactly this kind of strategy, if we have a mixture of sec and tan, we're either going to try and turn everything into tans and pull off a sec squared so that we can use this sub, or we're going to turn everything into a bunch of sec and then pull out a sec tan and then use this identity, right? So just play with this and figure out for yourself what are the powers that you need for this to work. But in truth, if you have this coming up, you're going to have a rather easy example, most likely just with sine and cosine. So no need to go overboard with these topics. The earlier topics, they will be tested, but you won't get the most exotic example. If you are, hopefully all of you are planning to get an A, I think it's worthwhile to just have your bases covered and know how to do the sec tan. But if you're just planning to pass the course, you'll most likely find just being able to do these very simple examples with sine and cosine. All right, cool. So that's trig integrals. Then we learned about trig subs. So let's try and squeeze this in. Trig subs. So this is when we had square root of plus or minus a squared plus or minus x squared. And then we had to choose some x is equal to a, and then one of three things, either sine, tan, or sec. And the point was to use this identity or this identity to kill the square root, right? So if, for example, we had like this, then our natural option would be to use this guy and let x be a tan of theta. Okay, and then when we put in this thing, we can pull it out, the a squared, and we'll have 1 plus, oops, I missed a squared sign here. Tan squared. We'll have a squared bracket 1 plus tan squared, which will turn into sec squared, and we'll have something squared, square root, which kills the square root. Again, do not try and memorize, just be aware that these are the three guys, and then you have to use this identity to simplify it, and you'll quickly come up with the right one. Now the problem with, or at least the complication of doing this, is that when we do it, then our dx changes. We're going to get a more complicated factor. So dx by d theta, we're going to have to place everything in terms of theta, and we get a more complicated factor because we have to differentiate this guy. So we're going to have a sec squared of theta. So the dx will be replaced by a sec squared d theta, which is definitely making things more complicated, but at the price of killing the square root, and we really hate square roots, so that's what we'll do. Okay, so then you're just going to have a trig integral, which is the stuff you just learned previously, and you're going to do the trig integral, but then you'll have the answer in terms of theta, and you have to turn the answer back in terms of x. And the way to do that is to unwrap your identity as a triangle. Let's try and squeeze that in. So if this was identity over here, what do we have? We have that tan of theta is equal to x over a. And we want to, the answer will be some function of theta, but we want to turn it back into something in terms of something in terms of x. So think about what tan is. So unknown angle is theta, and tan is the opposite side divided by the adjacent. So if we let x here be the opposite side and a be the adjacent, then this guy will be x squared plus a squared. And then we can read off what all these other trig functions of sine will be. So sine is the opposite divided by the hypotenuse. It will be x over square root of x squared plus a squared. So if our final answer involves sine theta, then we'll just replace sine theta by this thing. If it involves cosine theta, then the cosine is the adjacent divided by the hypotenuse, so cosine of theta equals a over this thing. And again, we're perfectly happy because now that's a function in terms of x. So this is rather a kind of heavy machine to do these trig subs. You might see this. Again, I expect a more easy, well, you will see this, I expect, but a more easy example of this. Yeah, so be ready for it. Okay, let's erase the board and do some more. Okay, the next integration technique is rational functions. So this is where we have the ratio or the quotient of two polynomials, p of x over q of x. Okay, it's called proper if the degree of p of x or p is less than the degree of q. And if it's not proper, you can do long division and make some expression like this, the sum of an ordinary polynomial plus a proper polynomial. So we have to just basically deal with proper polynomials all the time. And then there are various cases to deal with. So cases. It depends on what we can break up the bottom into. If we can break it up into distinct linear factors, so distinct, oops. So Q can be written, for example, as whatever, x minus a1, 3x minus a2, blah, 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 whatever, something like this, whatever, 7x minus a9. These are all distinct linear factors, right? So then what we do is we write this thing is equal to the sum of a over the first linear factor plus b over the second linear factor plus c over the third linear factor and so on. We make a common denominator by multiplying through, and then we solve for all these coefficients we've introduced. Okay? If we have repeated linear factors, then we have to introduce new coefficients. We're going to have to introduce an a and then an ax where the factor is repeated. It's quadratic if it's quadratic, and then so on if it's cubic, and so on and so on and so on. We also have to deal with the case when we can't break this up into distinct linear factors and we have an irreducible quadratic. then we're going to have to introduce an ax plus c above the irreducible quadratic, and then we also have a repeated irreducible quadratic. So it's many cases. Again, since it's the final exam, I think if this is examined, you'll only have to worry about the simplest case, which will just be distinct linear factors. So if we had something like this, like 3x plus 2 over x minus 2, x plus 1, then this is proper, and then it's going to be like this, x minus 2 plus b over x plus 1, and then we'll make a common denominator, a of x minus, or x plus 1 plus b of x minus 2 over the common denominator, and then we'll get rid of it, and we'll get equality of this top thing. So we're going to have 3x plus 2. Put together all the powers of x, so we're going to have a plus b of x, and put together all the constants, we're going to have a minus 2b. Okay. And then with this itself gives two equations. So the powers of x have to agree. So we just have one power of x, just 1. So this will imply that a plus b is equal to 3. And then the constants have to agree. So this implies that 2 is equal to a minus 2b. And then we can just solve the a and b. And then this expression here are things we can integrate. This guy, it's just a of log of x minus 2. And this guy, it's just b of log of x plus 1. Right? So that is proper. That is rational functions. Do some examples, be ready for it. Okay, improper integrals. Okay, there's two particular kinds we have to learn. There are, well, hopefully we have learned. There are the kind when we integrate from a to infinity, or to minus infinity of some function f of x. And this thing has no meaning. Infinity is not a number. Do not treat it as a number. This thing only means the following. It means the limit as capital R goes to infinity of a to r of this thing, if this limit actually exists, okay? Because this thing is an actual integral we can calculate, it makes sense. So that means that. It has no meaning otherwise. Do not, please do not just treat it like an integral. It's not. Infinity is not a number. In the early days of calculus, people were not careful about this. They were kind of sloppy, and often you can get away with treating infinity like a number, but other times you just can't, and they got false results. So this is why this emphasis on being very careful about what you mean when you define things comes around. Everything builds on top of itself with math. So if you have something which is nonsensical and you build on top of it, you just build this tower that's going to collapse. So it's important to do this. It's important. We're not just being fussy. It will actually give you wrong results unless you think of it like this. Okay, so that's that. And the key example is this thing. It's the integral from, let's say, 1 to infinity of 1 over x. dx is the limit as r goes to infinity, integral from 1 to r, 1 over x, and happily we know the antiderivative. It's the limit as r goes to infinity of log of r minus log of 1, which is 0, which is actually infinity. So this thing does not converge because this thing does not exist. The limit does not exist as a number, even though we can write the limit as infinity. So it does not converge. Let's draw a picture. So this is what 1 over x looks like. We are 1 at 1, and it's decreasing like this, right? So this is 1 over x. Now, if you try this, where we do the integral from 1 to infinity, 1 over x to the p, if p is bigger than 1, it will converge. And that's another easy calculation. And it kind of isn't surprising because if p is bigger than 1, since x is bigger than 1 itself, then 1 over x to the p will lie underneath this guy, right? So this will be 1 over x to the p bigger than 1. So it does have a chance to actually converge. If it was on top, then obviously it wouldn't. It would have more area, right? And if p is less than 1, then it's indeed going to be on top because we're going to take a root power of a number bigger than 1, which will be smaller than the number itself. So that has no hope to converge. So 1 over x is the kind of key cutoff. If you're underneath 1 over x, you're okay. If you're above it, you'll have no hope. Okay, so that is the first type. The second type is where we have a vertical asymptote. So for example, where we have a function defined from a to b, and it blows up like this. Okay. So it has actually no value at b. This has just got a vertical asymptote at b. And then we define this limit. So define the integral from a to b of f of x dx to be the limit as, let's say, tends to b from below of a to of f of x dx. Now for r, which is less than b, this thing does make sense, right? So this would be our r. So this thing right here, colors too similar, this thing right here is the area that we are calculating, okay? And as we let r increase, we're gradually going to get the entire area underneath the graph from a to b. And that indeed could be infinity. And again, there's a key example, and the key example is again 1 over x, right? So running out of space, put it over here. Key example. F of x is 1 over x. So as we integrate, we'd like to integrate from, say, 1 to 0. And this thing has no meaning except as the limit as r goes to 0 from the right-hand side. And it happens to be infinity. So r goes to 0 to r dx, and it's infinity. Okay. So the area underneath this 1 over x graph, let me find the place to put this. So 1 over x looks like this. Okay. And this guy has got infinite area underneath its graph from 0 to 1. Now, it's the key example as well, because if we consider different powers, so if we take p, which is between 0 and 1, then since x is between 0 and 1, then x to the p is the root power of x, and therefore it's going to be bigger than x, right? So if we take the square root of 1 over 2, right? Or better, 1 over 4. Take the square root of 1 over 4. Then what is that going to be? That's going to be 1 over 2, right? Which is actually bigger than 1 over 4. So the square root of a number which is between 0 and 1 will actually increase it, which is also what we just know from the graph, right? It's bigger than 1 over 4. Really squeeze for space here. So the square root function has a curve like this. In fact, any root function has a curve like this, right? It's a concave curve. So if this is the line y equals x, then the whatever root, square root, third root, whatever, will always be bigger. You can just see it from the graph, right? So back to this guy right here. If we take the power from 0 to 1, then we're taking a root power of x, and it's going to be bigger than x itself. And therefore, 1 over x is going to be bigger than 1 over x to the p. So 1 over x to the p does have a hope to actually converge, and it actually does, right? So 1 over x to the p, change colors to blue, 1 over x to the p lives like this. It is underneath. Okay, so 1 over x to the p, 0 less than p less than 1. So this time, if we take p between 0 and 1, it's underneath the graph and it will actually converge. On the other hand, if we take p bigger than 1, then x to the p is now smaller than x, right? So 1 over x to the p is now bigger, so it will lie above, so it has no hope to converge. So it's kind of the opposite. Well, it is the exact opposite of what happens as we take the improper integral from 1 to infinity. With the improper integral from 1 to infinity, if p gets bigger, then this thing goes underneath, it has more chance to converge. For the improper integral from 0 to 1, if p gets bigger, then 1 over x to the p gets bigger still, and therefore won't converge. But if p gets smaller, if p is between 0 and 1, then it does have a hope to converge, and it does converge. So this example and this example, which are the same function just on different pieces, are the key examples. Neither of them converge, but you just need to be underneath them in order to converge. Underneath them in the sense of a power function underneath them. And you can figure out what will be underneath it. So clearly, if p is bigger than 1, then 1 over x to the p will be underneath, and it will work. And it's a little bit harder, but it's not that much harder if we have 1 over x to the p, where p is some number which is between 0 and 1, then that will be underneath, and that will work. So that's the way to learn this stuff. Just understand the key example of 1 over x, and you just need to remember that when you have a power that puts you underneath it, you're okay. And you can calculate it a few times to convince yourself, but that's it. So be good with these two examples, which are actually the same function. Be good with these two examples, and this entire topic, improper integrals, will be rather easy. All right, let's keep going. Okay. First, I erase the board. Okay, the next topic is arc length. So if we have a function we might want to know the length of this one-dimensional curve, which is the graph, right? So this would be A, this would be B. And this is the first time I started talking about the Riemann sum machine. The Riemann sum machine is just that you cut things up into very small pieces where they're very simple. So let's first consider what happens when we have a very simple function. So if we just had a function from A to B, which was, say, f of x was any constant you like, say constant A, plus some kind of slope, like let's say b of x, so it goes like this, right? Then this wouldn't be hard, because what would we do? We'd just draw a triangle like this, and up like this, and we know that we're going along by this quantity b minus a, and since the slope, bad choice of b, let's not call it b, let's call it c. Let's call it c. And since the slope is c, that means we're going up on this part you can't see on the top of this board, b minus c. And therefore, by Pythagoras, this part right here would be just the square root of this thing squared plus this thing squared square rooted, right? Which would be 1 plus c squared b minus a, right? So in a very simple case, then we can do it, right? And the point about, I mean, this is one of the key points in calculus, actually, that we have the ability to look at things in a very, very small scale where they're differentiable, where basically the picture looks like this, right? And we have the second ability, which is to add things up, which are not conventional adding of a finite number, but adding over an infinite set of points, adding over every x inside an interval between a and b. So if we just had like numbers a1, a2, a3, then that's ordinary addition. You've learned that from early childhood. what you learn when the integration is that there's a more sophisticated way to add, where you don't just add things which are labeled by 1, 2, 3, but you can add things that are labeled by x, where x is everything between a and b. Okay? And that is called integration. And that allows you to look at things in a tiny, tiny scale for every tiny little bit above here, and then add them all up and take the limit. And this is like the kind of yin and yang of calculus. I mean, these seem like very different ideas, looking at things locally, looking at the slope, looking how simple it is, and then this new kind of addition. But they work in concert with each other and allow you to calculate all kinds of things. Yeah, it's fundamental theorem of calculus is exactly that. It's the yin and yang of very small regions being understandable, or understanding something on a large scale by adding its behavior on a very small scale with this new kind of addition, this new, more sophisticated version of addition. So that's what we do to get this formula. So the formula, and I implore you to draw the kind of pictures I drew in class, and I've done several examples like this. Work through the Riemann sum machine yourself to convince yourself that this is the formula. This is what you get. If you look at everything on a small scale, break it all up, and use this simple geometric idea, and then you'll have a Riemann sum, and you pass the limit, you'll get this expression here. And this 1 plus c squared, you can square root, you see it here, because f prime is the slope, right? So this is not a hard thing, and you need to understand it, not just be able to apply it. You need to understand it. That's the valuable thing. And even if you're just interested to pass the course and get as good a grade as you want, you need to understand it just because the amount of times people who sit exams, try to memorize things, just produce just nonsense, utter nonsense. So please take my advice and draw these pictures, look back in your notes, figure out that this is the correct formula. Once you have this, then you just do an integration. And it'll be a simple integration because there's a square root. So there's not many cool things we can do with the square root. We just have two or three techniques. One of them is trig sub. That's kind of a painful one. Another one is just to do a u sub inside the square root. That's a less painful one. Sometimes there's some algebra we can do where the stuff inside the square root actually is a square. So the actual examples of calculating these things are pretty limited. They're all set up to be one of the three kinds, usually just one of the two kinds, not including trig sub, of integrals with the square root that we can do. So the real thing to do is to have this formula down. Okay, so have this formula down. This is an easy topic. Okay, we went from this to surface of revolution. So surface of revolution. Now this is where we have, I'll use the same graph, we have some function from a to b into r, and we're either going to rotate around the x or the y. Again, I imagine you're going to be tested with the simplest version, which will be integrated around the x. So if we take this piece of surface and integrate, and rotate this thing around the x-axis, we're going to get a kind of cylindrical two-dimensional shape, right? And our job is to find the surface area of that, the two-dimensional surface area of that. And again, it's the Riemann sum machine. What do? We look at a little piece like this. So imagine just rotating this little piece around. We'll form a band, right? It'll be a band. And if this here is x, then this height over here will be f of x, right? So the issue, let's blow up this picture over here. The issue is, what is this quantity right here? Because this is the thickness of the band, right? And by exactly the same arguments as this thing over here, the thickness will be given by some expression like square root of 1 plus f prime of x, and then times whatever this is, so delta of x. Okay? That will give you the thickness. So if you do that, cut up in little pieces, think about the thickness of the band and the circumference of the band, you'll get the surface area. So it'll be the circumference, which will be 2 pi f of x, times the thickness, which will be this thing times delta of x. You pass to the limit, and you'll have this following formula. And you go from A to B. So 2 pi f of x, that's the perimeter of the band. And then this thing, 1 plus f prime of x squared. That's the circumference of the band. Again, draw the pictures, look back at your notes, convince yourself that this is the correct thing. And then, again, it's going to be rather easy because the integrals that can satisfy these things are rather limited. You'll just have 2 or 3 examples to deal with all the time because the square root's a pain. And again, easy topic. All right, that's surface of revolution. Okay, now we start to talk about sequences and series. Now this seems like a big jump into a totally different direction, but it all connects. So, let's put it down. So, sequences. So, what is a sequence? Well, it's just a collection of numbers that we label like this, A1, A2, A3, and so on and so on and so on, right? And this goes off to infinity, and the way to understand it, of course, is to draw a picture. So here's 1, here's 2, here's 3, here's 4, and then just put a dot at whatever value you have here, right? So if A was like around 2, and put a dot here. If A2 was around -1, put a dot here. If A3 was 0, put a dot here. If A4 was a half, put a dot here. Just make a collection of dots, right? That is how to understand a sequence. Okay. Now, first and most important thing about sequences is to understand what it means to have a limit. And actually understanding the limit of a sequence is kind of easier than the general limit of a function. So the limit of an equals L means the following thing. It means that for some particular number, let's get rid of some of the stuff. For some particular number L, so this is L, if we draw any thickness, any band of any thickness around L, so take your favorite tiny, tiny number and draw a line just that much above L and that much below L, then if you write this, you are signing a contract saying that you can guarantee that all of your guys, AN, are going to be inside this band so long as you're allowed to choose some point along these integers where you start to count from that point onwards. So there exists some n where from this point onwards, all these guys are always going to be inside this band. And that n is up to you. Okay. So my metaphor in class for this is that imagine you are tasked with writing a computer program to calculate some specific thing, like whatever, the total weight capacity of a bridge. And you are told that the error of your answer is unknown at this point. So what the error is required to be is not known. It could be you need the error within 5%. It could be you need it within 2%. That is to be decided. So you need a program that will do it for all these different levels of errors. So you just do a program that will just get a better and better answer the more you iterate it, the more computer time you spend. So your boss comes to you and says, okay, it's 5%. So okay, well, that's going to take 7 hours of supercomputer time. And then you run it and you get the answer. It goes, no. Now it's got to be 2%. You go, okay, well, that's going to be 3 days of supercomputer time. So you run it and you get the answer. It goes, no, error is even more tight now. We need it to be 0.5%. You go, okay, no problem. But now that's a week of supercomputer time. If you are allowed to have all the supercomputer time you want, you can give your boss the answer to win whatever error he wants. You've signed a contract with him. You say, I've written you this program that will give you the error to win whatever you want if you allow me any amount of computer time I want to do that. This is signing a contract. You are saying, I can guarantee you that all of these guys will be within whatever error you want of L, so long as I'm allowed to start looking beyond some particular integer n. Okay? So if this, your favorite small number, is 1 over a trillion, then you say, okay, I can guarantee you all the AN are going to be within 1 over a trillion of L, so long as you just start looking at them beyond some particular number I'm the one who says which number it is. It could be 100 trillion, billion, zillion, whatever. From 100 billion, trillion, zillion onwards, they'll always be within that error you asked me to guarantee they are in. Okay? That is what this means. You're signing a contract that you can get all these AN within whatever error, so long as you're allowed to look far enough along the right-hand side. There will be no exceptions after n. Whatever error you want, it'll always be within this band after n. Okay? Cool. So this might seem like kind of a lot of words about nothing, but I promise you it's not. This is one of the absolute key concepts, and this is where people were confused in the early days of calculus and mathematics. That they weren't careful about what a limit meant, and got into all kinds of messes. So if you learn more advanced maths, you'll see a more precise way to describe this. You'll learn a language to describe exactly this picture. Is a better way to say it, and you'll see, hopefully, that this is a natural thing. Okay, so that's what a limit is for a sequence, and it's an easier thing than a limit for a function. We have some obvious things, reasonably obvious things, I hope. So if G is continuous at L, then the limit as GAN goes to infinity will just be G of L. And again, this is just a picture, so let's draw a graph of G. This could be L right here. And we know that these AN get closer and closer to L, so let's put little dots here to indicate these AN getting closer and closer. So what would be G of AN? It'll be something here, right? This is G of AN. This could be G of AN plus 1, and so on. And they are, sure enough, getting closer and closer to G of L. You can just see it, right? The picture just shows it to you. So this is often useful. We use this in a number of places. And that is the main thing about sequences, okay? You have to understand what the limit is, and this minor theorem. Okay, actually I know what's coming next. So the point about, well, one of the big payoffs of defining sequences is that we can define now we talk about series. So given a sequence A1, A2, A3, and so on, you might want to actually add them up, add up all this infinite number of terms, right? You might want to consider this thing. But the only way this is meaningful is as follows. It's the limit as n goes to infinity of Sn, where Sn is the partial sum. Okay. And again, this is an essential point. It literally means nothing except as the limit of the partial sum. So key example. AK is equal to minus 1 to the k. Then if we consider this thing, then the sum from k equals 1 to infinity of minus 1 to the k literally means nothing. It has no meaning. It's not infinity, it's not negative infinity, it's not any number at all. It's a literally meaningless expression. You can't give any meaning to this. Okay? It has no meaning. Okay, so if you think about it for a little bit, you'll come to the conclusion that the only way an infinite sum can make sense is when you take a finite sum and you're allowed to take more and more terms. So if when you take the first billion terms, then it's some number. When you take the first 100 billion trillion terms, then it's some number which is kind of similar to the last one. And then you take the first 100 billion trillion zillion terms, and it's get ever close to some number which was a bit like the first two. And the more terms you take, the more it's tending towards some particular number. Since we have the concept of limit, we know what that means, and then we can give meaning to this expression. That's why we say the series converges, because we have to define it in terms of a limit of partial sums. It has no meaning otherwise. Okay, cool. So this is a very, very useful and important thing, and there are a bunch of results that we will learn about when these series converge, or that we have learned hopefully. And there are two kinds. Well, actually there are more than two kinds, but the initial thing we have to discuss is about when we have just positive terms. So suppose ak are bigger than or equal to 0 for all k. Then we can draw a picture to represent this rather well. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. And then draw a block whose height is A1. And draw a block next to it from 1 to 2 whose height is A2. And then draw a block from 2 to 3 whose height is A3. And so on, all the way across. Let's do a few more. Then the area of all of these blocks added up from 0 to infinity, or from 1 to infinity, is exactly this quantity, the sum from k equals 1 to infinity of ak, right? Because the area of each block, the area of the kth block is just ak, right? So we can visualize what this thing actually is. Okay, this would be A5. And if we want to understand when this thing converges, well, clearly the size of the blocks have to go down to 0, because otherwise the area would be infinite, right? If you just considered the partial sums as just taking a sequence of steps, then if all of these steps were positive and bigger than some whatever number, even if it was very small, if every single step you took was bigger than 1 over 1 million, but you just kept taking steps, then you're going to go off to infinity. You're not going to converge, right? So the only way this thing can converge is if the terms go down to 0. But the issue is that enough? And the answer is no. Because we have a key example again. So consider the sum from k equals 1 to infinity, 1 over k. Then if we consider this example, this guy looks fairly good to begin with. This is 1, this is height 1 over 2, 1 over 3, 1 over 4, 1 over 5, okay? But if we consider the function g of x, which is equal to 1 over x plus 1, then what do we know? Well, then g of 1 is 1 over 2, so it is here. So this is g of 1. G of 2 is 1 over 3, which is here. This is g of 2. So this is 1, this is 2, this is 3. G of 3 is 1 over 4, which is here. And so on, right? So g is a nice decreasing function. So if we just connect up these dots like this, we see that g lies nicely underneath the graph, or nicely underneath all of these blocks right here. Yeah, even right here, it's like this. So the area of all of these blocks has to be less than the integral of this guy from 0 to infinity, and that thing is infinite because it is after you change u to be x plus 1. You see it's just integral of 1 over u from 1 to infinity, which diverges, right? So integral 0 to infinity, g of x dx equals the integral from 1 to infinity 1 over u du, which diverges equals infinity. So even though these step sizes are going nicely in a regular way down to 0, if you keep taking step sizes of size 1 over k, you're actually going to go off to infinity, which a priori is quite a sort of surprising or strange thing. Imagine this was like some kind of paradox, some kind of puzzle that you read in a book before you knew any calculus. It could almost be like some sort of philosophical puzzle. Imagine a guy taking a sequence of steps where the kth step is a step of size 1 over k feet, right? Where does the guy end up after taking infinitely many steps? And the answer is actually he ends up in infinity. But if you change this a little bit and you sum 1 over k squared, then the answer ends up in some finite place. And the reason we can answer these questions is because of the power of calculus, because we can actually integrate functions, because we have the fundamental theorem of calculus. And if we didn't have that, then trying to understand what would happen to this guy would be really, really tricky, right? It would be really a struggle. So we can understand what's going to happen to sum from k equals 1 to infinity, 1 over k squared, with a very similar kind of thing. We are going to draw these blocks. So the first one is 1, the next one is 1 over 4, right? So it's 1, this is 2, and this is 1 over 9, and so on. But now consider the function f of x equals 1 over x squared. This guy just lives like this. When we are 1, we are 1. When we are 2, we are here, 1 over 4. When we are 3, we're 1 over 9. So this guy lives on top. But the integral from 1 to infinity, 1 over x squared, dx is indeed finite. It does converge. So if your step sizes go down like 1 over k squared, then it converges. So imagine you had like some very smart like cousin who was 12 years old, and you gave him this as a paradox. If he knew no calculus, he would not be able to answer this question. Right? He would not be able to answer what happens as you keep taking steps if the step goes down like 1 over k squared, and where k is the number of steps you've taken, as opposed to what happens when you go down a step of 1 over k. And it would be infuriating, right? It would be infuriating because no matter how much you would think about this, you just couldn't figure it out. You could like calculate it. You could add the first 100 terms, but that really wouldn't tell you anything, right? The first, I mean, if you try this, if you put this into a computer and just sum it, then it looks like it converges. It'll, depending on the size of the computer, it will produce some number that will gradually grind to what looks like a halt. The digits will slow down. It looks like it's converging. But that's just because the computer can't store that amount of numbers inside its RAM. It's such a kind of a good test of the power of the computer. But if you just let the computer run and run and run, whatever you think it's converging to, it's going to actually get bigger than that eventually. And then, in fact, in the early days of computing, people thought this was a magic bullet, and they just tried to calculate everything, including trying to sum divergent series. And it looks a lot like you're getting an answer. And then things will be built based on these nonsensical answers, which is one of the reasons that you have to, it's one of the reasons you're learning this stuff. If we didn't have to worry about it, if it was so straightforward, we could just program into computers and people would just press buttons, then there wouldn't be tens of thousands of people learning this stuff. But it isn't so straightforward, and you do need to understand it. Okay, so this guy diverges. This guy converges. And the thing what we've done here to understand it is something called the integral test. We found a function that has particular properties. So put these words here. If we have a function f which is decreasing, and f of n equals an, then n equals 1 to infinity converges if and only if the integral, now I can take any number I like here. I can take, let's just call it not a, let's call it m, or any number bigger than 0. Because the convergence of a series doesn't care about the first number of whatever number of terms, the first 50, the first 100, the first million terms. So, so you can start n equals 1 for this question, you can start n equals 50 or 100 or a million, and you can take m to be any number as well. I don't have to be the same number at all. And the reason this works is because of these pictures I've drawn. So this f is exactly this f that lived on top of the graph. So if this thing converged, then the area of all these blocks is underneath the graph of the function f, so it has to converge. And if this thing diverges, then just shifting it forward by 1, like this, would produce something which is underneath the graph. So if it diverges, the blocks, start again, will produce a graph which is underneath the blocks. So if it diverges, the area underneath the graph is infinite, and therefore the sum of all the blocks have to be infinite. So very, very natural test once you draw these pictures. And that's one of the key things we have to understand. And it also gives us the so-called p-test. That the sum from k equals 1 to infinity 1 over k to the p converges if p is bigger than 1 and diverges otherwise. Just because this integral of 1 over x to the p converges if p is bigger than 1 and diverges otherwise. Cool. So that is our first test for whether or not something converges, and it gives a good flavor of what's going on. So it's not enough that the terms go down to 0. They have to go to 0 fast enough, and a very powerful tool for understanding that is just to turn this question into whether or not some integral of a function f converges, where f recovers the sequence an, f of n equals an. Cool. Alternating series. So a series is alternating if it's of this form. So some k equals 1 to infinity minus 1 to the k, ak, where ak are bigger than or equal to 0. Okay, that's an alternating series. Sometimes we have a minus 1 here just because we want to start with a positive step forward. Really is not important. We just factor by minus 1 from this thing. Okay, so again, we're going to visualize this. What is this? This is what happens when we take a step forward by something of size a1, and we're going to take a step backwards by something of size a2, and then step forward by a3, and then step backward by a4, and then so on. Now, this guy is a different guy because in this case, we don't have to care about how quickly the AK goes down to 0. If they don't go to 0, then obviously this thing can't converge. We're just going backwards and forwards forever. It has no meaning, in fact. But if AK plus 1 is less than AK, and the limit as k goes to infinity, ak equals 0, then this thing does converge. And it even gives us an error estimate. So, should we write a sentence? Call this S. Then S converges. And we even know that S minus Sn is less than an plus 1, where n is capital N. Sn is the partial sum, k equals 1 up to capital N, minus 1 to the k, ak. And this again is just a picture. So in class we had a demonstration, we had Max and someone else whose name began with M, standing up at the front here. So this was Max, and this was the other student. And this was where we were at the Sn step. And then we take this step forward by step size an plus 1 to get to this other place here, right? This was, I think it was Melanie or something. These were our two students. And then we noticed that the next thing we would do would be go back by an plus 1, but we wouldn't go back as far as we were at step size Sn, right? Because an plus 2 is less than an plus 1, right? So this is where we'd be at step size Sn plus 2. And then we go forwards, but now with step size with step an plus 3, which wouldn't take us as far as where we were before. And then we'll go backwards, then we'll go forwards, then we'll go backwards and forwards. And we're trapped all the time between these two people, right? No matter what happens, we're always trapped between these two, right? And since the size of the step goes down to 0, that means we're trapped closer and closer to some particular value. So this thing is going to converge. Somewhere here will be whatever the actual sum is. And the gap between the Sn and the actual sum is less than the gap between Sn and what happens when we add an plus 1 to Sn. Very visual. So this is somewhat fast. She did a video on this, I think. So look back at this, and you'll see that this estimate's very natural. So this is how we estimate the errors, which is a very useful thing to do, because as you learn more and more math, you'll find that there's less things that you can actually explicitly calculate as a number. But if you can approximate it where the error is something you control, that's just as good as actually having the number. So it's a powerful theorem, and this is something that was tested in the midterms, and I hope will be tested, because this is such a key thing and it's a rather natural thing. We also had an error estimate from the integral test, which was the following. So I should have said that. So if we take the Sn partial sum, so we sum the first block, the second block, up to the n block. So these are all our blocks, right? Okay. Then, if we want to know the difference between Sn and the actual entire series, then it's all these other blocks to the right of it, right? So this will be n plus 1, and so on, all these other guys right here. But we can approximate how big they are just by this function that we have going through the corners, which is given by f of, well, has the property that f of n equals an. So this thing is the integral test, okay? So this thing is less than, should at least have consistent colors. This thing is less than the integral, look at the picture, from n, capital N, to infinity f of x. Don't try and memorize where it comes from. Draw the picture. You can just see it. So this is where Sn, of course, is the partial sum from k equals 1 to n of the terms ak. right? And S is the entire sum, k equals 1 to infinity ak, and this is called integral test from error estimate. Okay, let's go back to this. So from this theorem, we just need to have that the ak go down to 0. So example, if we consider this, the sum from k equals 1 to infinity minus 1 to the k, another completely key example. Oops. It satisfies the conditions. So then we have that ak is 1 over k. It's definitely decreasing. It's definitely going down to 0. And this thing converges. So converges. Okay. So we have a different ballgame with an alternating series. We no longer care about how quickly you go down to 0. And this often confuses people because you've been so trained that the sum of 1 over k doesn't converge. You look at this and you think, I'm not going to get tricked. But that's because you're not thinking about what this says. You're just memorizing symbols. Do not memorize anything here. Think about what this says. This is an alternating series going backwards, forwards, backwards, forwards. It's a completely different thing than when something 1 over k, which is just taking a sequence of steps forwards. Right? And this thing will converge. This brings us to different notions of convergence. So, absolute and conditional convergence. Converge. Okay, so given series AK, we say it converges absolutely if and only if the sum of the positive terms converge. If it converges but doesn't converge absolutely, then we say it converges conditionally. Running out of space. Okay, so it is a theorem, and not a very hard theorem, that if something converges absolutely, then it converges. Okay. So converging absolutely is a more special thing than just converging. An example, I just rubbed it off, of something which converges conditionally is this series, the sum from k equals 1 to infinity minus 1 to the k over k. Because for sure this doesn't converge absolutely, because we know the sum of 1 over k doesn't converge. But it does converge still, right? So therefore it's converging conditionally. So the way to visualize this is you consider this big blob as a collection of all series that converge. Then inside it there is a subset, which are those that converge absolutely. Okay? So this is series that converge. Okay? And those guys which still converge but do not converge absolutely, these are these guys in red, which we will say, well, not that we will say, but these are the guys that converge condition. Okay, cool. And there are definitely some of them. So this guy lives in here, right? Cool. Whereas if we had the sum of, k equals 1 to infinity of minus 1 to the k over k squared, then that thing converges absolutely. Right? It converges by the alternating series test, but it also converges absolutely. If we put the absolute value, we just get the sum of 1 over k, which does converge. So this guy lives in here, converges absolutely. Cool. All right, so these are the notions of absolute convergence or conditional convergence. Okay. Good. Keep this picture in mind. And we'll talk about some tests to determine when things converge absolutely. The ratio test and the root test. And what these guys are somewhat crude tests to determine if, ignoring all the superfluous details of a series, if a series at its heart is actually a geometric series. So this is the ratio test. I need to write it again. That's just stated. So if we have that the limit as n goes to infinity of the absolute value of an plus 1 over an, this limit has to exist and it is less than 1, then the series k equals 1 to infinity ak converges absolutely. If this limit is equal to 1, then it says nothing. That way. And if it's bigger than 1, then it diverges. Okay, so what's going on here? So this is the key example. So if we let an be x to the n, right, then an plus 1 over an is just x, right, or mod x. Yeah? And then this thing, an, is just the sum, which will converge if and only if mod x is less than 1. Right? So if you have a series where, when you consider the ratio of the an plus 1 over an terms, this tends towards something less than 1, then morally it's like a geometric series, because each term is just some fraction of the term before. So this test is determining if it somewhat, underneath any superfluous details, looks like a geometric series. So example, if you have something like this, n to the 3 plus 6n plus 12, but then it's over 2 to the n, you might think, okay, well, this n to the 3 plus 6n plus 12, that's going to mess things up, right? So that might prevent it from converging, but no, because 2 to the n is an exponential function, 2 to the x is an exponential function just applied to the integers, which will kill every other polynomial. So when you just plug that in, you take the limit, I'm not going to do this because I'm running out of time, you'll just find the limit of this guy is just equal to a half. So try it for yourself. This limit as n goes to infinity, an plus 1 over an is just 1 over 2. Because morally this thing really is just the geometric series 1 over 2 to the n. And that stuff here is just superfluous detail. Okay? So that's what the root test is doing. The ratio test does, that's what the ratio test is doing. The root test is doing something very similar, except it's doing a different way to determine. So in this case, we do the limit as n goes to infinity, and we're going to do the nth root, an plus 1 over a. Sorry. I'm getting tired. We do the nth root of an, and that's our limit. And again, think of an being mod x to the n. And then the nth root would just give us x, and again, it's a different way to determine if at its heart it's a geometric series. If the limit is bigger than 1, then these terms are not going to 0. And this is a good point to talk about the divergence test. So divergence test given a series n equals 1 to infinity an, if the limit n goes to infinity, doesn't matter what kind, if it's alternating or any other kind or positive terms, but if the limit an is not equal to 0, so the limit either doesn't exist or is not actually equal to 0, then diverges. And think about taking a sequence, infinite sequence of steps. If every now and again you take a step of some significant size, then you're never going to stop moving, right? You're never going to converge to some limit, because once in 100 trillion years, you're going to take a step and just move away to whatever you're converging to. So this is a natural theorem. The converse is false, and this often causes problems for people. Converse is false. It is not enough for the terms to go to 0, as we've already talked about. Think this guy. These terms go to 0, but this thing diverges, so this definitely is not true. Okay, so these are very useful tests, but they will often just tell us nothing. So if, for example, we have an is 1 over n squared, and we take this thing, again, this is a calculation, do it for yourself, this thing is going to tend to 1 as n goes to infinity. You can almost just see it in your head, right? But it does converge. And if we took an as 1 over n, the limit would still be 1. And it doesn't converge. So the reason is that these guys are not geometric series in their heart. They're converging or diverging for different reasons. So it's only useful if you happen to have something that at its heart is like a geometric series, like this guy is. But when you do, then this quickly gives you the answer. Okay, cool. Let us okay. There's a couple more topics which I'm just going to skip over. So there's the comparison test, which is a rather easy test. This is for when you have positive terms. Okay, maybe I'll skip over. So if we have an and bn bigger than or equal to 0, and bn are bigger than an, then converges implies an converges, which again is just a picture because the blocks that represent the bn contain the blocks that represent the an. And for exactly the same reason, if the sum of an, or series made up of an, diverges, then the series bn diverges. This is a useful thing. I mean, classic example is something like this: the sum n equals 1 to infinity cosine of n over n squared. It's a pain to try and figure this out, except if you remember the comparison test. So just note that this thing is less than 1 over n squared, so the absolute value of this guy converges by the comparison test, therefore the series itself converges. Okay? So that's this example. And there's also the limit comparison test, which is if we have that the limit as n goes to infinity of an over bn is some particular number L, which is bigger than 0, but is also less than infinity, then I like to say that these series are married. This is not standard terminology, but it's very vivid because once that is true, you're locked in together. Whatever an does, bn does. If an converges, then bn converges. If an diverges, then bn diverges. And that's often useful when you have some ugly series and you can't make sense of it, but you'd like to somehow simplify your life. So what would be an example might be this. So n squared n minus 9 over n, like 5n to the 3 minus 6 n squared. So this is an ugly guy, and you might think, okay, I'm not sure what to do with this. But if you just ignore everything but the leading order terms, then this kind of looks like just 1 over 5 to the n. And in fact, you can marry these guys. You can take this limit. And therefore, since this series will diverge, this guy will also diverge. And that's the point of the limit comparison test. So this is limit comparison test. Everything you can prove with the limit comparison test, you can actually prove with a comparison test if you make the right choice of thing to compare it to. But the limit comparison test often just saves you work. It's just a lot quicker. You don't have to worry about what's above or what's below. You just need to marry these guys. Okay, so that's the limit comparison test. All right, those are all of our tools. And somewhat like with integrals, we have a bunch of tools that we have to apply to determine if a particular series converges. And the series or which tool to apply will just depend on how much experience you've got figuring out which tool applies to which series. If you practice this, you will quickly find the right tool. Okay, so the point of learning all this stuff is to actually talk about power series. Which are series like this. Okay. And these are very powerful generalizations of polynomials. If you just took the sum from k equals 1 to any number, it's just a polynomial. But we can express many more functions if we take this infinite sum. And that's one of the key ideas of calculus. We can represent functions as this infinite series, this power series. And power series in the region where they converge are just as good as polynomials. So all the cool stuff you can do with polynomials, integration, differentiation, summing them, factoring things off from them, you can do for power series where they converge. So it's really great to be able to represent something as a power series. It's really a powerful thing. I mean, if we could, all the stuff we learned about integration just becomes redundant once we can represent it as a power series, because we can integrate it just term by term. So integrating a power series is just as easy as integrating a polynomial. So that's the point of power series. That's the point of these later topics, Taylor and Maclaurin series. But the introduction to this is just to consider this function, which is this guy. Okay? So this particular function, 1 over 1 minus x, has this power series representation. Right? And then we can do some algebra to turn other things into the form of 1 over 1 minus x. And since this thing converges in its range from x less than 1, it's a theorem that we can integrate and differentiate in the region which it converges, which means we can get power series of things that don't initially look like this. So the classic example is tan of x, right? Tan of x doesn't look of this form, but if we differentiate it, then we get 1 over 1 plus x squared, and that does look of this form because it's written like this, 1 minus x squared. And then we can use this expression here, so then we have the sum from k equals 0 to infinity of minus 1 to the k, x to the 2k. Okay, but that's just the power series representation of the derivative, but we can integrate this because we can integrate power series just like polynomials. So if we take the antiderivative on both sides, we have tan of x is equal to what happens when we integrate this thing term by term, k equals 0 to infinity minus 1 to the k, x to the 2k plus 1 over 2k plus 1, and we might get a constant, well, we will get a constant c, but in this particular case, when we set x equals 0, tan of 0 is 0, so there's no constant c, so get rid of it. And that's the power series expansion of tan that we just got from this, just by differentiating and getting into this form. We could also integrate and to get something which is in the form of 1 over 1 plus x, or 1 over 1 minus x for the right choice of x, and then power series expand and then differentiate to get back. So we can get power series on the cheap from this identity, and that's worth doing because in general, calculating a power series representation of a function can be hard, okay? But it's very important. So if we do have a power series, for a function, okay, so it's like the sum from k equals 0 to infinity ck x to the k, then we can actually figure out what these ck are just by doing fairly simple things. Let's make it more general. So if we just stick in x equals a, then all the terms will drop except from k equals 0. So we'll have that f of a will just be k0, right? Then if we differentiate this thing, we'll kill the constant term, and then we'll have f prime of x. Okay, and then it'll sum from k equals 1 to infinity ck times k x minus a to the k minus 1. And now when k equals 1, we get the constant term, so we'll have that c1 is equal to, I'll put it this way around, let me put it over here, we'll have that c1 is equal to f prime of a, and so on. If we keep doing this, let's put it over here, we'll find that ck is equal to f to the k over a over k factorial. So if there is a power series for our function, then we know what the coefficients have to be. And that leads us to this kind of interesting thing that if we look at the first few terms of the power series, so if we have the first term we've learned is f of a, the pen is dying. First term is f of a. The next term is f prime of a, and then x minus a. This thing is exactly the tangent line, right? This is just the tangent line that we've learned about lots of times. So this is the graph. We take the tangent line here. It is given by this formula where this here is a, and this is the function f. If we take the next expression, f prime x minus a. And this thing adds the ability to put a bend in the tangent line and do a better approximation. Oops, squared. And so on. So the Taylor polynomial, which is what happens when we take the terms from k equals 0 up to some particular finite n, that's the t-nth polynomial, is just a generalization of the tangent line. Okay? So all the cool stuff we can do with the tangent line, we can do with the Taylor polynomial. We can have this simpler function that approximates our function rather well over an interval. Cool. So there was a section we learned about on this. All right. Next topic. Okay, so we learned to calculate various Maclaurin series, Taylor series. One of the most powerful applications was to actually explicitly integrate things over some particular interval inside the interval of convergence and get an approximate answer with error as small as we like. So that was a rather difficult topic, but again, a very powerful one. It makes redundant all these difficult techniques that we learned previously to integrate functions using finding the antiderivative. This is a general machine that gives us an answer which is as accurate as we like. I hope that's examined to some extent, but if it is, it'll be a rather simple manifestation. So if that's some part of the course you find the hardest, then don't stress about it too much. But for sure, Maclaurin series, Taylor series are some of the very most significant and important things in Calc 2. So expect to be tested on these things. Expect to be able to calculate Maclaurin series of certain functions, recognize Maclaurin series of certain functions, explicitly calculate certain kinds of series, because you see it's just putting in some number into the Maclaurin series of a well-known function. These are the kind of examples you've been practicing in homework, so expect to see something like that again. Okay, after we did this, then we jumped somewhat into the beginning of multivariable calculus by discussing parametric curves. And these were curves where we sent t to x of t, y of t, which is a point on the plane. And I suggested you think about this as plotting the motion of a bee, right? Or some other object or some other insect. And think of t as being time. And the point about this is that we can create a function that does something like this, that goes over this set of points, this curve in the plane, whereas if we just have a function from R to R that satisfies the vertical line test, we can't have a set of points like this. Okay? So we started to learn about parametric curves, and we started to do some calculus of parametric curves. So calc of parametric curves. So what did we learn? We learned to sketch them. We learned the slope of the parametric curve. So the slope is the dy by dx slope. And how did this make sense? Well, we drew pictures, and we found that this made sense just as x prime of t over y prime of t. Okay, so I put this in quotation marks because nothing is a function of x, but if we just looked on a small scale and tried to understand the slope of the tangent line of this guy, it turned out to be this. Again, it was just pictures. This allowed us to find points on the parametric curve where the slope was horizontal or vertical, or equal to some particular angle, or to say what the slope is at some particular point in the parametric curve. We also learned the arc length of the parametric curve. And this was just given by the following. Now we're integrating with respect to t, so it's from, say, t0 to t1. And by exactly the same pictures as we drew before, using Pythagoras' theorem, it looks like this. It looks like x prime of t squared plus y prime of t squared dt. Okay? Exactly the same pictures as before. We also learned about the surface of revolution. Of parametric curve. And again, piece of the parametric curve, say between, let's not do this piece, let's do this piece here, and then if we rotate it around the x-axis, we have to think about the circumference and the thickness of each little band that makes up this object, and A and B is a bad choice. So let's call this thing here x of t0, y of t0. And let's call this particular point right here x of t1, y of t1. Then we learned that this thing was the surface of revolution. We have to first account for the circumference of the band, so it's going to be 2 pi y of t, that gives the circumference, and then the thickness of the band, which is this thing. Again, everything is pictures. Do not try and memorize this stuff. Just draw the picture. Okay, dt. Cool. And then, final topic was polar curves. Or polar coordinates. Okay. So polar coordinates is a different way to represent points in the plane. So we represent points in the plane by an angle from the positive real numbers and a number r from the origin. Okay, and initially we're going to take the angle to be positive and the r to be positive. Okay, and that uniquely defines this particular point here. And later we learn we can take r to be negative, and what that means is exactly the mirror image point over here. So minus r of theta is defined to be equal to just r of theta plus pi, the exact opposite point right here. So this is minus r of theta. And then we can also have negative angles, but that means we go clockwise instead of anti-clockwise. So minus angle phi is this angle here. This is minus phi. Okay. And then this thing, this new coordinate systems, allows us to describe curves where the radius is some particular function. So we did some things like this. This was a cool guy, right? So this guy produced this kind of flower shape, like this. And you will probably be tested. I mean, this is a new topic which hasn't been tested on any midterm, so very much expect this in the final. And you might be tested on identifying what picture corresponds to what polar curve. I would say sketching a curve, but not on this exam, obviously. So, well, I think it would be unlikely that they find a way for you to sketch a curve. But you will have to be able to recognize it. So you'll have to sketch the curve in order to identify which picture is the correct one. And then we did some calculus of polar curves. So what did we do? We learned how to do the dx dy slope of a polar curve. So dy by dx slope of polar curve. We learned how to find the area underneath some loop of the polar curve or some part of the polar curve. We learned to find the arc length of the polar curve. And that just came from the arc length formula for parametric curve, because we can just define this thing from a polar curve, and that gives us a parametric curve and gives us this stuff. Okay, so that was the last 15 weeks of calculus. It might seem like a lot, but there's this effect in math that as you understand something, its size compresses. So if you have been studying consistently, this doesn't actually seem like such a huge amount of content. You'll have it in your head, and if you don't understand this seems like a massive amount of content. So if you're feeling like this is a lot, then just keep working, keep studying it, look over these things, don't lose momentum. You will understand these things. You will feel like it isn't so bad if you just keep pushing at it. Okay, as I keep saying over the last 15 weeks, there's no substitute for time in this subject. You just have to not become discouraged, not become stressed, just keep thinking about it, trying it. Watch my videos, watch whatever piece doesn't seem to make sense to you. Try the homework questions again, do the auto-autoed exercises, obviously do the past exams and the practice problems. Keep working right up to the day of the exam, and hopefully things will go well for you. Okay, that's it. Have a good summer.